Hi everybody. I think this week we'll be continuing with the CPU instruction sets, part 2. Last week we have a very brief discussion on the types of assembly language and register transfer notations and so on and so forth. And this week is basically a continuation of that, but probably we go in just a little bit deeper. So this week we'll be continuing with the addressing modes and some of the instruction sets, particularly those that deal with actually stacks. Okay. So topic covered this week will be stack pointers. We already know what is actually stack. Stack is basically a stash of memory allocated by the programmer to perform certain functions. Okay, so stack in itself, there is actually being applied for the CPU cycles, and we're also going to cover some addressing modes. Now, these addressing modes will be able to relate back to the last week tutorial. There are 5 questions. Maybe we can reflect back which register addressing mode are we actually talking about. The 5 questions, A, B, C, D, and we are also going to briefly cover what is orthogonal CPUs. Okay, it's something to do with addressing memories, right? Hold on. Go. Okay, so stack is a specialized volatile memory segment used for temporary storing of data. So this one, I think we've given a lot of examples as we cover the class GPS coordinates, probably temporary data, IMU data, probably variables, very common example, variables. Sometimes we do program and we can use instead of just one memory slot, maybe we have when we define an array, normally it's configured as a stack. Okay, so stack is managed with stack pointer, both by programming or by CPU itself. Data is stored in this segment with transaction called push. Okay, so you have 2 assembly language that deals with this. One is called push, one is called pop. Any stack transaction uses a stack pointer which points to the address where push or pop is to be realized. So stack pointer, we've covered this in the earlier parts of the lecture because stack pointer is actually used in the computer cycles as well. If you still remember, the fetch, decode, execute, fetch, decode, execute, and there's a program counter, and this program counter, stack pointer, and all this actually works together in the CPU for the operation of the computer cycles. But what about in the case where we need to define a stack? Okay, how will we know how to actually use it? The term stack was coined in analogy with tray stacks. Okay, if you have those office tray stacks, first in, first out, you know, the tray stacks, you document, you put in first, out. And because of the analogy, we have several other computer terms that actually associated with this concept of stack. Of course, you have first in, first out, last in, last out, last out, last in, first out, first in, first out. Okay, so these are common computer terms that deals with actually memory. Okay, this means that because the computer actually uses embedded system actually uses LIFO, last in, first out. Item on the top is the last one to put there. That's why the content of the stack is usually called top of the stack. Okay, so the top of the stack will be removed first. So if you store, let's say, 5 variable in a stack, okay, last in, first out, the 5th one will be the first to be popped out in this case. Okay, so just remember these terms called top of stack, before, and so on and so forth. After each operation, the stack pointer is updated with a new top of stack. So after you either you do a push or a pop, the top of stack value actually change. Okay, indicating that the next one to be pop or push. Okay, this information will be passed to the stack pointer. In most MCU architecture, the stack is used or compiler defined, and it usually goes downwards, not upwards. Okay, this means that the stack pointer contents diminishes each time a new item is pushed onto the stack. This one we will see a bit more example, then we understand. If in words doesn't visualize so well. Okay, now let's assume that the arrow is actually pointing to the top of stack. Okay, and once you perform an operation, either push or pull, the top of stack actually changes after pulling. Okay, new top of stack becomes 7. Okay, so the arrow indicating the top of stack, and this top of stack referring to the memory that is about to be pushed or pop top of the stack. Okay, this information will be passed to the stack pointer. Since stack pointer is precisely related to top of stack, we refer to its content as top of stack. No problem. Okay, so the stack pointer is basically a volatile register that stores the top of stack. Okay, it's easily as defined as that. The user or the compiler may define the stack segment by initiating the stack register. So when you're doing a programming, you can define the stack, and then after you define the stack, you can initialize what is the content of the stack pointer register. So depending on the microcontroller, the stack pointer will contain top of stack for push and top of stack for pulling. It doesn't matter, more or less the same. All right. The case will determine how the push and pop operations are physically performed. It will determine how the programmer may read. Okay. So what are the two main instruction sets that affect the stacks? Okay. So if you study last week, there are a lot of assembly language, and most of them actually deals with jump, arithmetic, logic, or whatever. In this case, in the category of moving, transferring information, there is this push and pop that is designed specifically for stack. Okay, so these two are reserved for very specific purpose, deal with an array of memory. Okay. Now let's look at now it's very confusing. Push, push, pop. You basically just understand these two. Basically push, and then there's pop. Some textbooks they have this term called pull. It's more or less the same. Okay, so the source, when you perform a push, this is what happens to the stack pointer. Okay, the source will be entered into the stack pointer, and the stack pointer will be it'll be indexed by the stack pointer, and the stack pointer value will decrease by n. N is the the amount of information, the bits that you're considering. Okay. Okay, I think just now I mentioned push, pop, and pull. It seems that these three are actually distinct functions. Okay, ignore what I said. I think I got a bit confused with too many programming language that I'm learning at the moment. So you just ignore. I think at the moment we accept it as this push, pop, push and pop, push, pull, pop. There are three distinct instructions. Okay. So in the case of pop, you can see that this operation is performed first, followed by the content pointed by this stack pointer. So you can see that this one is loaded first, and then it will be stored in the current stack pointer minus n. Okay, while this one, it will, for pop, it will minus first, then it will be stored in whatever the content of the stack pointer. So you see this 2 is just the what happens at the end of the instruction. So the question can actually come out in a bit tricky information. Say that we push A1 B6. Okay, what will be the content that? What will be the address that contains A1 B6? Okay, so if it's a push, if it's a push, then it'll be this. Okay, after this operation, then only you -1. It will be directly referenced to the stack pointer value. Whereas in the case of pop, stack pointer will be decreased first, then you save your content to the value of the stack pointer. So in this case, of course, for 4 and 8 bits MCU, n is equals to 1. For 16, 2. For 32, maybe 4. Okay, it depends on your memory size. Okay, for your memory, some have a very big memory, so that's why 4 and 8 bits can be 4 and 8 bits is 1, 16 bits 2. It depends. Okay. So have a look at this example from textbook, example 3.11, stack process for 16-bit. It's illustrated. Again, this is textbook. There's a lot of questions that actually can be associated with just this push and pop operation. Questions might ask you what happened to this memory, what will be the content of this memory after you perform this push or pop, all right? So 3.11 shows this value. Is again to show you the example of push and pop. Okay, so push your you push this value. Stack pointer initially is 027E, and whatever that you want to push is in register 9165. Okay, so in the case of push, let's see, push. You just remember push. In the case of push, this one will be loaded to stack pointer. After you load, then the stack pointer will be decreased by 1. Okay, so you see again, you load, and then stack pointer will be decreased by 1. Hold on. Okay, I think it's correct. Yep, you load first, then the stack pointer will be decreased by 1. You just have a look at this example. If the values are changed, you guys should be able to perform the same operations. Okay, so the content goes in, then the stack pointer reduced by 1. Okay. Example 3.12 from the textbook. This time the operations are done for 8-bit. Okay, stack pointer n equals to 1 for updating. So the memory is at 8-bit. That's why n equals to 1. So you can see this is the initial value push. You put the value, the ACCA value, and after you perform the push, this will be what happened to this memory. Observe which memory is being updated. Is it 027E or 027D? Okay, so you need to determine all this because questions can come out to assess whether you actually understand this concept or not. Okay, so observe for push and observe for pop. Okay, what happens first? Okay, so this is the initial value, both are initial value, and after the push, what happens? Okay, you can see that the content are exactly the same, except that now for pop, the stack pointer it goes up. Okay, so refer back to this slide. Okay, for pop, stack pointer goes up. Okay, in both example, the original content of the memory location is lost during a push. This does not happen during a pop. Okay, so you can see that push means stuff actually being pushed inside the stack, whereas in pop, it remains. Okay, it remains after you perform the push and then you perform the pop. in POP, the memory in the stack remains, but whatever that you want to pop to, that register will actually change. So in this case, the ACCA value changes. Initially is 5A, but after you pop last in first out, okay, you pop this value, ACCA will be 2FH. Okay, so have a look at this. You should be able to do this after you study this week's lecture. In both examples, the original content of the memory location is not lost during a push. This does not happen during a pop. Okay, in a pop, it remains. Whatever that you have, it remains. But whatever that you pop to, that particular register actually change. Okay. So regardless of how the architecture is and how top of stack is defined, the RTN notation is as such. Remember source destination last week tutorial. I think we discussed on this register transfer notation. Okay, so this register transfer notation, we can also see how is this operation, is it an immediate, indirect, and etc. etc. So even in the user does not utilize push and pop, they may occur transparent to the programmer. Okay, so why do we use push and pop? Okay, so we can actually access information, but push and pop, they may occur transparent to the programmer, even if the user does not utilize push and pop. They can happen in subroutines interrupt which require special subroutine called interrupt service routine. Okay, so subroutines are program modules logically separated and independent from the main program. Okay, so these are, you can think of it as I think you're just about to enter this lecture called interrupt service routine. Okay, so it's basically like a program that can be interrupted, and then you also have functions in embedded this assembly language. You have an equivalent of a function in assembly language. It's called subroutine. So subroutines are invoked to do specific tasks and then continue with the main program with the instruction following the call or interrupt. So in this subroutine, function call or interrupt service routine, let's say for example, you are running embedded system blinking LED, suddenly the user interrupts. So that particular routine is called interrupt. Now when you interrupt the main program in your main while one loop, what happens is that there is something that needs to be passed to the stack. Okay, there's a stack reserved for this kind of subroutine. When you this actually slide is actually talking about the application of stacks in subroutines. Okay, you might not be aware, but just like the computer cycles, every time this is invoked, this interrupt service routine is invoked, you're running a while loop blinking LED, suddenly the user key in. Okay, so that is an example of interrupt. And when you interrupt the main program, what happens is that you need to utilize the stack to return back to the original scenario before the main while loop program is being interrupted. Okay, so why do we need to interrupt? Okay, so interrupt happens, for example, your Windows system is running program whatsoever, but suddenly the user actually key in some values to change the flow of the program or whatever. This case we need interrupt because the user pattern is unpredictable. So we can come in to key in something at any point. That's why you need to use a interrupt service routine. Alternative is pooling, but pooling is not very efficient. Okay, so pooling, you need to check the status for the peripherals. Let's say, for example, you need to check in the while loop. You need to have a routine to check. Okay, keyboard is being utilized or whatever. Then you actually service the keyboard. Now, example of a subroutine. RSR or function, utilizing the stack, okay, the main program, and then you have your subroutine, then you actually go back. Now we bear in mind that every line in the program is basically an instruction. And when your main program is interrupted, the PC needs to go back to the state before it was actually interrupted. Okay, so how do we do that? When a program calls a subroutine, the current content of the PC is pushed onto the stack. So there is a stack reserved for this PC. The contents of the program counter is pushed on the stack. Before executing the call instruction, the PC contains the address of the next instruction to be fetched. Now, bear in mind, read this a few times, because questions can come out, for you to explain what happens during a subroutine, what is being pushed, what is being popped. Okay, so by pushing the PC onto the stack, CPU is effectively storing the memory and the address instruction following the call. Before the call, okay, the stack needs to contain the information to go back to the original state of the main program before the call. Returning from the subroutine causes the PC to be popped from the stack so the program execution can be resumed. So after you've done the subroutine, let's say for example the user have done everything, okay, that's done. You need to go back to the LED blinking program. Now, how do we do that? The PC program counter will pop back from the stack before your execution of the user interruption. Okay, so this is a very important element to look into, how the embedded system will actually take advantage of this stack to do its subroutine. Okay, so instead of an accumulator or whatever values, now you have your PC. Okay, so a stack pointer is here. Okay, now stack pointer is here. PC equals to next. When you run the subroutine, the whatever that's in the PC containing the next instruction, okay, will be pushed to stack pointer. Next, whatever that's here, next is the next instruction. Okay, it could be any instruction. If you're executing this instruction, the next one to be executed is normally stored in the PC. So once the address is being pushed to the stack pointer, now the PC is free to contain any instruction. So the PC will really contain the will contain the instruction for the subroutine. And after you do the instruction for a subroutine, once the subroutine is completed, the PC will actually resume back. It will contain back the value of the next instruction set before the main program is actually interrupted. So this one, look into this. What happens to the individual pop and push and pop and push? What happens exactly to the stack pointer and the register that is involved? Push is for putting things on the stack. Pop is for pulling things on the stack. Okay. So this is just the instruction. What happens to the is an explanation of what happens here. Okay. So I think I've roughly explained to you. Just before the call, stack pointer is pointing to +8. So this is an indexing way of accessing the memory. After step 1, after the call instruction is fetched and decoded but still not executed, PC will point to the next instruction. The execution of the invocation result the current PC value being pushed onto the stack and loaded with the start address of subroutine 1. So this is the new subroutine. It could be an interrupt subroutine, it could be a function or whatever. Now the instruction to be fetched is 1 in the subroutine, so it changes. Subroutine are executed in sequence and return to the instruction. You have a RETI, return instruction, equivalent to your return in your C program. When the return instruction is executed, the PC is popped, restoring the value next, which is allow the execution of the main program to continue back. Okay, so after the subroutine is being performed, stack, okay, you put back the original value inside. And then we have this thing called addressing mode. Addressing mode can be defined as the way in which an operation is specified within an instruction to indicate where to find the data. Okay, so we've talked about register transfer notation. we haven't actually discussed on what type of addressing mode, how you configure the memory. Let's say you have an instruction. I think, for example, the most simplest assembly language. Go and read in your textbook. MOV, move. You move a value from one register to another. Now, short one, a quick one. This move instruction set falls under which category? Okay, it falls under the category of instruction sets that has to do with data transfer. You have arithmetic, and then you have instruction sets that affect the flow. Okay, so one associated with flow program is like jump, enrich data. Okay, so this one we've discussed a bit. Whether it's jump or whatever, you can actually utilize the different addressing modes. There are various ways of doing information transfer. Okay, so we're going to look into that. Okay, so now one of the way to do it is using immediate mode. Means to say that move, register, and then you have this value. So the value itself, using this hashtag, this value itself is being transferred to the register. So if you say that move R9 and you have a hashtag number, let's say some numbers, random number 215 or something like that, this value will be stored in the register. So it's as simple as the immediate mode. Okay, so the syntax is hashtag number. So if you move register hashtag number, this number will be stored in the register. And then you have, this one is the most common one, move, let's say R1, R2. You move the content of R2 into R1. So it's register to register. The example is your question number 1 in your last week tutorial. So this is a register addressing mode where the content of R9 is transferred to R8. So it's a register to register. An example is move R8, R9. Okay. And then you have your absolute, or what they call direct mode. Okay, the number is the address where the datum is located. The number is sometimes referred to as a symbolic mode. So you can identify from the last week tutorial. I think it's move R9, and then you have a value. Let's say, for example, R6 C5 H. Okay, so no, sorry. Okay, move. You have your bracket, and inside the bracket RC65. Okay, and then you have your value R9. So whatever value in R9 will be moved to whatever that value in the bracket. So RC69 or whatever. Okay, so when you see a bracket, the value of what is indexed by that bracket, pointed by that bracket, that is the value that will be stored there. Okay, so if you have a move bracket, let's say 1111 H and then comma R9. So whatever the value in R9 will be stored to 1111. Okay. And then you also have indirect. Okay, found in memory location where address is given by contents of the register. Okay, so this one, remember last week we covered some tutorials where is indirect. Okay, so the values, sorry, this one not bracket. Let's say, for example, memory. Okay, last week I think it was question number 3, 3, 4, 5. Okay, so you have indirect. Memory location address is given by the contents of the register. So you use an alias sign when you deal with this. So when you have a move alias register and comma R9, so R9 will be stored in whatever that contained in this register 9. So let's say Rn. So let's say that Rn points to some value, let's say 1112H. So the information from R9 will be stored to 1112H, not Rn. Okay, so let's say Rn is 1116H, R9. Move alias Rn, comma and then R9. Okay, so the value will be stored in whatever that's inside the address in Rn. So Rn, the content of Rn will be treated as an address. Okay, this is different from indirect. Okay, and then you have index. Okay, you have you can have where X address plus the contents of register. Okay, let's say for example you have an address 256A, something like that, and then you have Rn. So Rn, if the value of Rn is, let's say, some values, so this value will be indexed. You plus X plus whatever value in Rn, and this value will be stored in that particular address. Okay, let's say for example, you have move X is an address, and then you have Rn, comma R9. So R9 will be stored, whatever content in R9 will be stored in the address X plus whatever value in Rn. Okay. So this is addressing mode and jump instruction. How can we utilize particularly this index? Okay, how can we utilize? Sometimes you want the instruction to jump. Okay, you skip certain instruction. So this instruction will allow you to be used by having this offset. So you have this the program counter equals the program counter plus an offset. Okay, so this is an way of doing index. Index means in C programming, you +1, +2, +3, you keep skipping. So you can do that for your program counter. Okay, you plus an offset where this offset can allow you to skip certain functions. Okay. Now CPU is said to be orthogonal if all register and addressing mode can be used as operands. Sometimes many designers prevent the use of special register as operands to prevent unexpected result. It will be more flexible if you can use the registers as operand. Most probably not. Can you think of a special register? Okay, if you've done your lab, okay, you've opened the IAR, you know that R2 is a status register. Can you use that as an operand? Let's say, for example, move R9, comma R2. R2 is a status register, we know. Okay, it's called SR. Can we do that? Okay, in the case of orthogonal, yes. But in typical case, non-orthogonal CPU, you cannot do that. Okay, so I think we will come back with more examples on assembly language. I hope that you guys study this. Again, this week is a bit rush. I'll be recording the lectures for this because I have some important issues that I need to take care of in our station. So any questions, you can WhatsApp me, all right? Whether you don't understand or you want me to repeat this lecture, please feel free to let me know. Thanks.